The obsession with multivibrators and today's high inflation got the Lion Kingdom thinking about the 1970s, mainly how to extend the multivibrator to a more sophisticated display. It led to creating a complete LED animation with just transistors like the 1970s. 40 years ago, Lions wanted to make an animation out of 5mm LEDs placed side by side. We only had red. They were all dim and diffuse. Microcontrollers were expensive, and the documentation was nowhere. A very skilled hobbyist might have had TTL logic and a book of datasheets. But all us normal Lions would have were discrete components from a Radio Shack down the street. It was actually normal for animals outside China to have access to electronic components down the street rather than mortgages. Lions 40 years ago only knew about the mighty bipolar junction transistor, but not how to connect them. What if the components we envisioned doing animations with 40 years ago would actually do the job? To make it not be a complete waste of time, this version would use modern LEDs. The heart of an LED animation is a sequencer that lights up one LED string at a time. Here we have the analog sequencer, and the simulation showing all 9 states lighting up at the right times. Nowadays, you'd immediately think of a shift register and an oscillator, but that would take a lot of transistors. Shift registers on the internet take around 4 transistors per bit. The simplest analog solution Lions could think of was the delay switch. A delay transistor starts on. A delay capacitor slowly raises the base voltage of the delay transistor until it shuts off. The capacitor asymptotically approaches the base cutoff voltage, but never quite reaches it, so it needs a pull-up resistor to go to the power rail rather than the base voltage, while the base gets a current limiting resistor. Then we have a second transistor, which turns on the next delay switch in the sequence. The next capacitor will be ground, and the next delay transistor will start as on. The delay switches cascade until a reset pulse zeroes all the capacitors. A variety of test circuits were made to show the concept of cascading delay switches working. They used a multivibrator to generate the reset pulses. To save money, the reset pulse also determines the delay of the first state instead of a capacitor. The delay of the last state is determined by the start of the reset pulse. Thus, a sequencer for 9 LED states can be made out of just 7 complete delay circuits. To translate the delay switch outputs to current for the LED strings, we have a network of diodes and NPN transistors. The LEDs are enabled through complex diode logic, so multiple states can turn on the same LED strings. The problem is the NPNs turn on at 0.7 volts, while the delay switches use PNPs that turn off at over 4.5 volts. As the delay switch turns off, first the cascading PNP transistor turns on the next delay switch at 4.5 volts. Then the NPN transistor turns off the LEDs when the delay switch finally hits 0.7 volts. But we want them to switch closer together. A voltage divider is the key to raising the off voltage of the NPN transistor until it switches at the right time. The voltage division is a tricky measurement, depending on the load current and the voltage in the delay switch. Each delay switch in the cascade has slightly less voltage. Such are the interdependencies of a minimal component analog design. Instead of getting it perfect, we set them all to a 475 plus a 330 and lived with a slight overlap between each LED string. All the LEDs could be obtained from a cheap kit, which would have given similar brightness to 40 years ago, while having more colors. But if you're going to spend months paw soldering 210 LEDs, they might as well be modern super bright jumbo LEDs. The sequencer was fabric cobbled point to point, as it would have been done 40 years ago, to make a living schematic with all its wiring visible. The childhood vision was a line of LEDs stacked as close together as possible, but in the interest of getting a larger display for less money, the LEDs were spaced apart. A test of 20mm and 15mm spacing showed the line was harder to detect when they were 20mm apart. The 20mm spacing would also be too big to fit in the apartment, so 15mm it was. Down went an LED printout with the 15mm spacing. All 420 holes were poked, and the 210 LEDs were installed. One red LED was bad. The soldering was brutal. This part would be just as nasty with a microcontroller. Optimizing for the least current usage made a lot of weird series combinations. The Lion Kingdom already made a display with all the LEDs in parallel, and it took so much current it never happened again. It's much harder to supply high current than high voltage. The diode logic was installed as a single unit. Much voltage tweaking was required to get the LEDs a reasonably even brightness. The white LEDs were too bright and needed a separate voltage regulator. Finally, the sequencer was mated as a single unit. The multi-vibrator was fabricated and it started animating. While a modern display would just involve recompiling a program, there was much replacing of capacitors, resistors, and diodes to adjust the timing. The multi-vibrator ended up using a 2200 microfarad and a 220 mic for the capacitors. The delay resistors all ended up being 1.7K. Schottky diodes can't be mixed with silicon diodes for it to work. Some of the diodes were burned out. All the NPN transistors needed a diode voltage drop before the base. Without it, the sharing of base voltages with multiple transistors wouldn't balance, and only some of the transistors would turn on. It would be nice if the animation had more moving parts, but the Lion Kingdom accepted the fact that the moving parts occupy only a small part of the real rocket. A microcontroller would have eliminated most of the voltage regulators with PWM. It just shows that discrete analog is expensive. It shows the limitation of an analog sequencer, the very limited control of the animation, and the very few variations that are possible. One advantage is not needing any decoupling capacitors. We don't see any more sharp, saturated primary color LED displays like what existed 40 years ago. Modern displays are so focused on displaying video just because they can, that we only see washed out colors and soft edges. It's a shame to cripple such a large display with the limitations of a vintage analog controller. A microcontroller wouldn't have all the glitches and can do more tricks like folding the landing legs back up or different delays. The analog controller could be moved to another simpler display using just LEDs from 1980. Another problem is the rocket sequence doesn't repeat in real life. A better use for a looping sequencer would be something that naturally repeats.